Hello, everybody. My name is Aus Zra, and I will be presenting a simple and cheap design to implement the simplest quantum machine. So when I was thinking about doing this project, I asked myself, what's the easiest quantum algorithm to implement? Because I wanted to study the needed components to actually implement it. It turned out the Deutsch-Jozsa algorithm is the easiest one. It's the easiest algorithm that can show us quantum effect. Before we start, I want to mention that my main focus here is the cost. And every modification I did to this design was mainly to reduce the cost. Throughout this presentation, we will go over why do we even need to do this algorithm. We will show the relationship between the classical gates that we have on a single bit and try to implement them using the quantum circuits or the quantum logic gates. And then I will go to prove this algorithm using the IBM Qiskit Lab. And then we will look at the design that is published on an article from Nature and try to replace the components with cheaper ones to perform the same goal. We will estimate the cost that we need to implement this project, and then we'll discuss the expected results. Luckily, we have already studied this algorithm in chapter 5. The main reason why this algorithm is interesting is because it shows quantum supremacy over classical computers. That means it can perform something no existing classical computer can do. It can tell whether a certain function is a constant or not by only using single query, which means a single trial. In contrast to the classical computers that requires this number of queries. So in our design, we will use just one bit system, so n is equal to 1, and that means we will require here 2 to the 0 plus 1, which means we will require 2 queries if we want to do this on a classical computer, and on the other hand, we will need only 1 query, and we will show that right now. Just before we proceed, I want to mention that we already have a design for this algorithm on chapter 5. However, this 1 qubit system or 1 qubit Deutsch-Jozsa algorithm is actually very hard to implement because this controlled unitary operator requires performing quantum discrete Fourier transform, curl effect, and adjusting other parameters. The good news is we can implement the same algorithm using a much easier design. So here we're going to do a quick review on all the possible classical gates that we can perform on a single bit system. So we have 1 bit here, and we have these are the four gates that we can have. So the first one is identity, and like if we send 0 here, we will get 0 because there's just nothing. If you send 1, you will get 1. Negation is the opposite. If you send a 0, you can get 1, and vice versa. The first 2 are called changing functions and reversible functions in the same time, because wherever you have at the output, you can conclude the input from here. So if you have here 1, you know that this was 1. On the other hand, we have 2 functions that are neither reversible nor variable. So these are the constant functions. So a constant one means if you send 0, you will get a 1. If you send 1, you will get a 1. So we know that this is not something good to put on the quantum computer because the main condition that we have for quantum computers is that all the gates must be reversible, and this is not a reversible, which means if you have 1 here, you don't really know whether the input was 0 or 1. So these are the 4 combinations of the 4 gates that we can have. Now, the question that we want to ask is, if we are given a black box, so here we don't know what function is this, and we are asked to find whether this is a constant, which means these 2, or whether this is a variable gate. So to do that, we will need to send some bits and test them, right? So we might send like 0 and find the answer, and then send 1 and find the answer. One bit will not be enough because, say, for example, we send 0 and we got 1. We don't know whether this was the negation that changed it to 1 or whether this was the constant 1. So we always need here no matter which one we have here, we will need to send 2 bits, and we will need to do 2 queries, which means 2 trials. So that's for the classical computer. And the Deutsch algorithm that we just mentioned says that if we implement this using a quantum computer, you will still need to send 2 bits, but we will be able to do that using only 1 query, not 2 queries. So this will be the quantum supremacy, and this will be where we will see the quantum effect in action. Now, let's try to implement the same circuits that we did, but now using quantum circuits, not classical circuits. So on quantum, using a quantum gates, let's do constant 0. And this is the system here. The system means I have something here to send. So this is the function I will send, whether this might be 0 or 1. And the output is actually here. So this might be confusing first, but the input is here. This is the input, and this is the output here. This one here is only shown because we don't want to lose the reversibility. Remember, if we put something constant here, we will lose the output that we will lose the input. We will lose the information. So we are just putting this just to maintain whatever we have here, just to stay here. So neglect that for a moment. It's not our main concern here. So in the second bit, we will just send a fixed 0 all the time. So let's now try to construct the constant 0. And it might not be a surprise that we already have it without doing anything. So what does that mean? So the input, no matter what's your input, whether you send here 0 or you send here 1, the output is connected to the 0, so your output is always 0. So this is the constant 0. We already have it. Now let's move to the constant 1. If I want to make a constant 1, I will keep the same design. I will just put here a negation, a quantum negation. Remember, if you forget that, this is like this. So I will put the quantum negation, and that's it. No matter what you send here, whether it's 0 or 1, the output is actually only linked to this. So this is 0, and 0 will be here. For the negation, it will be flipped to 1. So you will get always a constant 1. So to make the constant 1, all you have to do is just to put the negation. Let's do the identity. Identity means if I send 0 here in the input, I should get 0 at the output. And if I send 1, I should end up having 1. And to implement this circuit, all we need to do is just to put a C0 gate control node. So let's see how will this work. So if you send the 0 here, the 0 will have no effect on the C0. So this 0 here will stay 0. So the 0 will give me 0. But if I am sending 1, I'm sending a 1, the 1 will change the control bit. The control bit will change the target bit. So this 0 will become here 1. So I will end up having 1 out of 1. So this is indeed the identity. This is how the identity works. Now the last one is the negation. And we know that if we have the same thing as the identity, but adding to it a negation at the end, you will have, if you send here, let's say 0, this 0 will not be affected here. So it will be here flipped to 1. And if you send 1 here, the 1 will flip this 1. So you will get 0. So this is for the negation. So far we got all of these for gates. And now let's ask ourselves, if we want to implement this, what are the required gates, quantum gates that we need? So we need the C0, and we need the negation. That's it. We just need to figure out how to do these two. One disclaimer I want to make here is that the idea for this design is not mine. It's from a YouTube presentation named Quantum Communication by Microsoft Research. So the idea is to make this design here, to put 2 Hadamard gates before and 2 after, and to put whatever we have here, to put the function that we want to measure. And the claim goes like this. If you put these designs here, so let's say you want to put the identity here, on this black box, or whether you want to put the constant or any one of them without you knowing which one is inside of this black box. Uh, if your answer is the same thing, like 1 and 1, that means you had a constant function. So it might be a constant 0 or constant 1, but you will know this immediately with only one query. If on the other hand you got a 0, 1, not 1, 1, that means the one that's inside the black box is either the identity or the negation, which means it's a changing function. So let's test that this is indeed the case. To do this, we will go to Qiskit lab and try to see the results. Okay, so here we have the Qiskit lab. And just a reminder, the blue ball means you have a 1, and the gray one means you have a 0. So this is the design, and we will place the gates that we developed here. So these are the 4 Hadamard gates, and we will put we will insert in between of them what all the gates that we have. So the first one was the constant 0, and if you remember, we said for constant 0 we don't put anything, so we will keep them like this, and we will get 1 and 1. Actually, you can test that easily because this 0 is becoming here 1 because this is the NOT gate. So you have 1, 2 Hadamard in front of each other will cancel out. So you will end up just having 1. Same goes for this one. So nothing, no quantum effect here. It's just a simple design. So now let's see what we will have if we actually, let's just go back quickly. So if we want to put the constant 1, we will just put an X on the bottom one. So let's put a negation here. So if I put a negation here, we will see that nothing changed at all. So although this is getting negated, but the Hadamard is returning it, and when you take the measurement, it's still a 1. So that's the fun thing here, is that either if it's a constant 0 or constant 1, either way you are ending up having 1, 1. So let's see if this is the case when we put the changing gates. So we will delete this one. The identity says just put a C naught, and for the negation add an X to this C naught. Let's do this. So if I put here a C naught gate, you will see that I have, so it might take some time. You will see that I have a 0, 1. And even if I add to this design a naught here, I will still get I'm supposed to get the same thing, which is 0, 1 again. See, it's 0, 1 again. So that's the biggest proof that this works. If you put a constant function, you are ending up with 1, 1. If you put a changing function, you are ending with a 0, 1. And this is all in one query. Remember, I'm not doing this twice. Although I'm sending 2 bits, but I'm just doing it in one time. This is the supremacy over the classical computer. Now let's discuss how to actually implement this design. So we will do the whole project using only optical devices or optical gates. So the first question is how to make all of these gates. So let's start with the NOT gate. What does the NOT gate does? So remember, if we are talking about optical, we're talking about photons, and we're talking about their polarization. So we either have a vertical or horizontal polarization. And to make a NOT gate is so easy. Just bring the half wave plate. What does that mean? That means it will rotate your phase by double the angle that you will put it on. So if you will put it on 45, it will rotate it by 2 of this number. So it will rotate it by 90 degrees. And this is what we want. So if you send a polarized light that's up or vertical, you will get, after the gate, you will get a horizontal. And this is the NOT gate. This is changing it from 0 to 1 and from 1 to 0. This is available on market to buy. We will discuss its price later. Now, the second one is the C NOT gate, control NOT. And this is by far the hardest one to implement. But luckily, I found on this article a demonstration of all optical quantum controlled NOT gate. It's from Nature. It's a very respected article, peer-reviewed. So I trusted their design. They have this design that shows how to make a C NOT gate. However, the design required here a single photon detector, and this is very expensive. And you can imagine if if you have only single photon, it's really hard to not get noise and hard to control it. But in my design, we will change this a bit to something, and we will still get the same goal that we want. The second thing that's very hard is the state preparation, if you want to send a single photon. So remember, guys, what we want to do here is just having either the 0 or the 1. So either 1, 1 or 0, 1 in our design. So why do we need a single photon? Actually, we can do it using like arbitrary number of photons. It will still work. So in my design, we will change this. We will change the single photon detectors to photometers. So the photometer is a device that receives the photons and will tell you how much the intensity of light is. And this is very cheap. I already have one. We will use two of them to measure the intensity of light. And this will be a good indicator. So if you have high intensity, we can consider this to be 1. If you have very low intensity, because it will not be perfect, you will always have error. So we'll consider this to be 0. And from here, for the state preparation, instead of preparing a single photon, we can just put a polarizer, a linear polarizer. I will show the demonstration in a second. So if I have, let's say, a vertical polarizer, here it will make all the unpolarized light become a vertical, and this is how I'm preparing the up state, and I can prepare here the horizontal state in the same way. So no need actually for that. And remember, all we want to do is just to send 1 and 1. So we just put them as two horizontal ones. Now, this the expected results from this apparatus is as follows. So this is the measured output here. So see, guys, this is the control node. If you got 0, 0, you are expected to get 0, 0 because this is not controlling the 0, 1. And this is expected. It's just as the other one. But if you put a 1, 0, let's say, for example, the expected thing is that when you put 1, 0, it will change this 0, the target bit, it will change it to 1. So you will end up with 1, 1. So you should get a 100% of this. But in reality, you get this much of this one, and you get this much of the error. But still, this is good for us, because as long as it's more than 50%, if like we got 70% by 30%, this is still good, because we know the 70% means 1 and the 30% will mean 0. In addition, there is one more thing we can eliminate from this design, which is the filter. So the filter is meant here to preserve only this light source that they are sending, which is 702.2 nanometer, and to reject any other photon. And the reason is because they want to make sure no other photon will reach here. And again, guys, our idea will eliminate this, because we are not really interested in one single photon. In our project, trillions of photons actually will pass, and that's okay, because what we will put here is a photometer to measure the intensity of light. While this is not a good approach in other systems that require tracking a single photon, but in our case, in our project here, we don't really need it. So this is a great relief. Actually, this reduces the cost tremendously. One more thing to mention is what's left here. We have the half-wave plate, and we say that this one is like a phase shifter. It rotates the phase. We need this. We need 4 of this here, and we need 2 more. So we will need 6 for our design. The quarter wave plate, this produces a circular polarization. We will actually need 4 of this as well. Not in this phase, but we will put them after the Hadamard gates. We will need to produce the circular pattern. So that's it for this one. As you can see here, this is the carry, this is the control, and this is the target. So let's say the target is 0, and if you send 0, you should get here the target here should stay 0, and if you should 1, it should stay 1. Implementing this is not really that hard. You just have to put them in the correct angles and in this shape.
you should get a controlled NOT gate.
So I will do a quick demonstration to show how we can use photo meters to as a photo detectors. So first thing we want to revise is the unpolarized light. When it goes through the linear depolarizing filter, you will get just the vertical polarizer. The other thing I want to go quickly before I show the demonstration is the concept of superposition. So let's say you have here unpolarized light and it passes through this polarizer. So if this polarizer is like this, all the outputs will be like this. So this is the output that you have. And this is the polarization state that you have. And if you now if you pass this through other vertical polarizers, so this polarizer is vertical, this cannot pass. So it either becomes a horizontal, which means the cat is dead, which means no pass, or it becomes vertical and it passes. So according to the classical interpretation, this is the Moore's law, which means you just put the cosine of the angle here and you will get the intensity of what will pass. But we know that this is wrong because this is assuming the bits here, I mean the photons will be cut in half, like half the energy will pass from here and half the energy will pass from here. But we know that according to this equation, Max Planck's equation, we know that the energy is integers multiplications of h times f, which means you cannot have half of the energy, half of the photon. So either the full photon will pass from this or it passes in this direction. And if it chooses to go to be horizontal, it will not pass. So this is why when we put this equation, we will have this 1/2, this one, and 1/2 the vertical, which means if you take the probability, which is the squaring of this function, you will get half of them will pass. I mean, half of them will pass this one and half of them will be blocked. So we will do this experimentally. A simple demonstration. I have the photometer here and I have linear polarizers. So as you can see, if I put them in phase, you can actually see through them. If I put them in 90 degrees, however, 90 degrees out of phase, you cannot see anything, it becomes dim. So what we will do here is we will measure how exactly the photometer is accurate for the light intensity. So here if I put them both in phase, and I will try to go away to not affect the measurement. So as you can see, it's almost 100. So now I will put them 45 degrees out of phase, and we should expect that 50% of the light will pass. Now that I made them 45 degrees out of phase, you can see that it's almost half of the magnitude that we had. And this confirms that we can actually use photon detectors photometers to make them as work as photon detectors. Okay, moving on to the Hadamard gate. So we all know that this is the Hadamard gate, and we need the Hadamard gate for our design. We need 4 of them actually, and it can be like the Hadamard gate can be thought of as the combination of these things. I mean, you won't put that on a quantum computer, there's no addition, but we can just say that we can think of it as being rotating 90 degrees on the x-axis on the Bloch sphere and rotating also 180 degrees on the z-axis. And this is Pauli X and Pauli Z. If we have such an apparatus that rotates them both simultaneously, you can see that you will start with something and you will end with the same thing. However, I tried to search for something like that, but I couldn't find. However, there is another way to implement the Hadamard gate, which is by using a polarizing beam splitter. This is a cube that can divide the beam that we are sending to it into 2 perpendicular directions. And it also splits the polarization. So let's say the S polarization will go this side and the P polarization will go to the other side. So this indeed performs what the Hadamard gate performs, because remember, if you send a 0 bit to the Hadamard, you will get half of it becomes 0 and the other half becomes 1, right? And this is what will happen here. If you send the S1, half of it will go to the S and half of it will go to the P. And you might be asking by now, then why didn't we use the polarizers that I just showed in the demonstration? Why don't we use them as Hadamard because they also give 50-50. And the reason is because they are not reversible, which means if you put two linear polarizers on 45, the output will not be the same as the input. On the other hand, if you put two polarizer beam splitters in this graph here, if you get input 1 and it goes through all things, the output 1 will be identical if you use it twice. Same goes for input 2, and this is proof why this will work. The last thing, after we discuss all of these gates that we need, we will talk about the cost to implement this. So I went online and saw what are the cheapest products. So, you know, for every one of them, there are different range of items you can purchase, and the cheapest one for the polarized beam splitter was 57. For the half wave plate that we need 6 of them for our design, the cheapest one was this much, and the zero order means that it does not control a lot of stuff like temperature and wavelength, and we don't really need this for our project. It's not relevant, it's not necessarily. Here we have for the quarter wave plate, the cheapest one was 121. So if you put all these together, and the photometer was $50, and if unless you use the USF lab, you need to buy the stands and holders. Overall, this project will cost you $2,400, and it might seem a lot, but remember, with this amount of money and with this design, you might be able to design a quantum machine that can perform something no existing classical computer can do. This is the references that I used. Again, most of the design was from this YouTube channel, so I don't claim this to my own. And thank you for watching. That's